Hi everyone, at Team Michigan, our project is to detect SNPs with a cheap DNA probe-driven test. This technique, called competitive SNP lamp, relies on competitive binding from a probe and sync DNA sequence, which results in differential fluorescence between a wild and mutant type patient. The current methods for designing probes explores a small set of candidates in the problem space. Additionally, the current method relies on thermodynamic fluorescent calculations. Through computational modeling, we aim to expand the number of potential solutions explored by using a more flexible approach. Additionally, we rely on hybridization affinity as opposed to fluorescent estimations. All of our work can be accessed in our GitHub repository, which has an MIT license. In this repo, you can find all of the required files and objects necessary to run our CLI. It is important to note that users must have Python installed along with NumPy, Pandas, Matplotlib, sklearn, and text distance packages. We recommend that when users download all of these files, they store them in the same directory. To download the files, click the Code button in the upper right-hand corner, and then hit the Download Zip button, which will download all of the files. Once you download all of the files in our GitHub repo, place them into a single folder. I've called this folder CLI Demo, and it's just for demonstration purposes. Once you've done this, it's time to input your files that you want to do the simulation on. I'm going to deposit 4 files right now. These files represent the unoptimized probe sequence, unoptimized sequence, a mutant frame, and a wild frame. The probe and sync sequences refer to the same genomic coordinates and are complementary to the mutant type and wild type frame respectively. The mutant and wild frame refer to sequences of their respective patients, where the SNP is located directly in the center of the sequences. Probe and sync sequences should also be less than half the length of their reference frames. With this information ready, we can begin to run our simulation. Our simulation runs via command line interface or CLI, so the first step in running a simulation is opening up a terminal window at the file location which you saved all of our GitHub repo files. The first command that we're going to run is called opt-probe. The first thing that we're going to do is we're going to specify that it runs via the Python 3 language, calling a function within this file, and the command is called opt-probe. We then pass in the probe sequence, the sync sequence, the mutant frame sequence, the wild frame sequence, and then we store the results in a file called simoutput.csv, the convergence in convergence.txt, and then we finally specify that the number of samples is equal to 200. This is a relatively small simulation, but it will work for demonstration purposes. Then just press enter and wait for the simulation to complete. You'll know when a simulation is complete when the next line in the CLI opens up for you to start typing. Now that we've run our simulation, we need to check that it's actually converged or worked properly. To do this, we're going to call another command called the physconv command. Again, we're going to specify the Python 3 language, this file, and then we're going to call the physconv command. To this command, we're going to pass the convergence file that we generated in the previous command, and then again, we're going to make another output file, which is a PNG type file. We set the resolution equal to 300, which is fairly standard for publication quality. We name the graph, and then finally we specify the height and the width of the graph. Once we press enter, it should work fairly fast, and now we can go to our folder where we should see a new PNG file created. If we open this PNG, we can see that the simulation follows a logarithmic-esque curve over time, which is what we want to see, and we do see that the convergence goes up and stays pretty high towards the end of the simulation, which informs us that the simulation has worked properly. We now know that the simulation ran properly. However, our simulation generates results randomly, and depending on the number of samples included in the simulation may generate a good deal of potential solutions. Therefore, it makes sense for us to organize the solutions in a logical way. We believe that the best way for solutions to be organized is primarily by loss value, and then after that, by the number of samples that reach the same convergence state. To organize results, we're going to use another command. Once again, we're going to be calling the Python 3 language, this file, we're going to be calling the rankres command, and we're going to pass our CSV file that we generated in the first command, and we're going to save the output to a new CSV file, which we call results ordered.csv. We can now view that file, And we can see that the loss values are ranked first, and then finally by frequency. At this point, we've run our simulation, have generated results, have ordered the results, and have validated that the simulation has run properly. However, it might be worthwhile to investigate how our simulation got to the conclusions that we saw. Therefore, we included machine learning analysis in our simulation. In order to use reverse analysis, first type this function in. Again, we're going to be using the Python 3 language, calling a function within this file, and the command is called revml. To this command, we're going to be passing in our ordered results generated in the previous command, and we're going to save the new results to a revml.csv. Finally, we list the indices of the rows that we want to include in this reverse machine learning analysis. Our tool uses zero indexing, meaning that the first row refers to sample number 1, and the second row is referred to as line 1. You can list any number of samples that are included in that file into this parameter. We can now check the results. And here you can see the results generated in machine learning analysis. What we want to see is that the NEC of the probe is higher in the mutant frame than the wild frame, and vice versa for the sync sequence. This is going to be the NEC for the probe to the mutant frame. This is going to be the NEC for the sync frame to the mutant frame. This is going to be the probe to the wild frame, and finally sync to wild frame. And the whole point of this is just to ensure that our simulation didn't blow up and the loss function was overcome by a particular value. And here we can see that this is true, and this informs us that our simulation ran properly.